Welcome to the Help Session 8. If you can hear me, let me know in the chat. If you haven't done this before, this is interactive and I'm expecting you to use the chat. So firstly, just make sure that you can hear me. Put something in the chat saying yes or no. Well, if you can hear me and if it's loud enough, if I need to change the volume or anything. Also, I'm waiting on that. Where's webcam viewer? There we go. That's there. That's there. What is going on? This should be working. This is working. Awesome. Let me also check the link up on. I might have thought it was. All right, so if you're here, I'll put a link on LMS. That's not. Would help if I had a color. Yeah. Say hi. The chat. Announcements. All right. For people, give it a couple more minutes while I put out the announcement. No editing time. Live stream starting now. That's the YouTube link. We should want the link. Live help. Beautiful. So we're just waiting for a couple more people and then we'll get started. Copy link address. Putting in an announcement on LMS. Beautiful. All right. So if you have any questions regarding the assignment, now's your time to put them. Else, I've got a bunch of stuff to cover. Cool. Just check that. Cool, that should work. First forum. All right, so let me go through what I plan to cover. So where's my pen? All right, so there's a couple of things that I plan to cover. So the first one I think we should cover, which is the easiest. Let me just move the chat. Sorry, wasn't as organized this time. Over there. All right, so we can do command line arguments. They're probably fairly easy to get out of the way. Then from there, we can do, let's say, files. We could possibly look at more preprocessor directives, which will help us not next week, but the week after, but they're handy to know. Processor directives. So they're like your macros and stuff. And there's one other thing that I wanted to cover. Yeah. flight order. Which is Indian. It's with an A, I think. Double check. Yeah, Indian. Indianness. Beautiful. All right, so these are the things that I want to cover in this stream. Unless you've got specific questions, ask them now. I will go through all of this, and I think this should be very helpful. I'm just thinking if there's anything else that I'm missing that we could do. All right, so we've got quite a few people now. That's excellent to see. So what we'll look at then is command line arguments. So basically, let's start here. Let's move up the screen. So basically, so far, every time we've run a program, we've always started it the same way. And that's with, save that. That's with main. So we've had something like int, void, sorry, a long day. Int main, and either brackets or brackets with void in there. And then inside of that, we've had all of our code, and it calls to other functions. And that's been pretty standard. Now, in ANSI, there is another suitable function that we can use for main. And this is this definition of main. Int main, int argc, char star argv, square brackets. So you can try this yourself. You can try and put those things in, and you'll see that it compiles. Okay. So you can see quite clearly that this is legal in C. But if you try and add 3 arguments or something like that, or you try and change these arguments, it won't work. Okay. So let's go back a little bit and let's have a look at our compiling. So let's move to another spot, and then we'll come back to this because this will help us. So when we compile our code, we write something like this: cc minus warnings all minus o program, and then the C file program.c. Okay. Now, when we have a look at this, this very first one is the program. Okay. This is the compiler. Okay. This is the program we're running on a text file to make it an executable. But the program is GCC or CC, which is the compiler. Now, with this program requires some information. It needs to know the name of the file. It needs to know what you'd like the executables file's name to be. It needs to know if you want warnings, etc. But what you'll notice is different about this program than your programs is that there's no prompt to the user. So it's not saying, would you like to see all warnings? Yes or no. What is the file's name? Please enter. What is the output name? Please enter. And our programs have been doing that the whole time. They've been printing to the user. But this program here, the compiler, doesn't have printing out to the screen and scanning from the screen to collect that information. If you try and run CC without anything after it, it will say no input files. Okay? So it's expecting you to know to include these things afterwards. And these are your command line arguments. Okay. Now, this is important because we want this same ability. Okay. We want our programs to be able to get information at the command line. So not from the user, but when we run them. So before the users even touch the program, before we've said, what kind of resistor is it? Is it in series or parallel? We don't care about talking to the user. We want to know right when we run the program what the values are. And so we want to pass this in with our arguments. Okay. So this new main that we've just introduced allows us to do that. Okay. The first argument here, the first parameter here is argc, and it's an int. So an int's good for counting, and that's exactly what it does. It's called an argument count. The second one is argv, and this stands for argument vector. Okay. Now, this here is an array of car pointers. Now, that's important because basically what it is an array of pointers. Okay, and we'll have a look what they point at in a soon. Okay. All right. So if we take our example of this here, the number of arguments, or the argument count here, is actually 5. Okay. It includes the command or the program's name as one of the arguments in the count. Now, argument vector will basically point each one of these to separate strings. Okay, so there'll be minus wall with the null terminator, and so on. So we get a bunch of strings here that are all of our command line arguments. And that makes sense because we've got car star, so we can point to a string with those. So this allows us to get information from the user, not from the user, from the command line. Okay, so let's do a quick example. So I'll get rid of this stuff, I'll get rid of this, and we'll write a very short example. So the very first thing that you'd likely want to do with your command line is to make sure that the user has entered, when you've run it from the command line, that you've entered the right number of arguments. So if we had a program here and we must pass in one argument, okay? So let's say our program is called, let's say it's called program, okay, or prog, and there's one bit of information that must come after it, okay? For example, that. Then we want the argument count to be 2, okay? 1 because we need our name of our program, but the other one because we need some information to come in via the command line. And so to check that, we can just write something like if argc is not equal to 2, then we might print I don't know, requires 1 argument. Now I know that the count is 2, But when referring to the arguments, we say that there's one argument, there's one command, but the count includes the command. Okay, so that's why we check for 2 rather than 1. Does that make sense so far? Okay, so we're just counting how many words are written after our executable name. Okay? If that makes sense, just say yes or a thumbs up or something in the chat. And then we'll keep going. All right, we're a little bit behind. Quite a few people. Just got a quiet chat. What happened to my chat? All right, so I might continue. However, I need the chat to be a little bit more active, or else we might have to end early. All right, so from here, because argv is an array, we can do something like this. We could go printf %s / new line, and I could go argv0, and that should print out the name of the program. That should print out prog. Okay, it's a string. Remember, it's a car star. Okay, so that there should print out our. See, you got there. Our string. Okay, so we'll do an example shortly. And then here, I'm going to print out another string because we're expecting 2 arguments. /n argv1. All right, so now I've got this, and let's say I compile it and call my program. Let's just put a return 0 here. Let's say I compile my program and run it, okay? And I write, when I run it, I write prog hello. Then this should check, is argc not equal to 2? Well, argc should be equal to 2 because when I ran the program, I added a space and added hello. So the number of arguments in the count is going to be 2. There's 1 argument, 1 command. 1 + 1 is 2. From there, we are now going to come down here because it's 2. Okay, so they are actually equal, so we don't go inside there. And then we print out our argument vector 0. Okay, which is the first string stored in this variable here. So this will print out prog. From there, we print out argv1, which is hello. Okay, so we can get strings into our program quite easily, and we'll need to use this for our lab this week. We're going to get a file name in from the user, and this is why we were going to cover files next, and then we can have a look at what this looked like when we actually use it for something meaningful. The moment this program doesn't do much, it just prints out the name that you ran and the word after it. Okay, but it's a nice, easy example to see what's happening. So let me know if you're up to this point, and then we can continue with files. And then we can come back to this with files, and that should give you a lot of stuff to help you with next week's lab. So if it's making sense, just let me know in the chat. For anyone that's new to joining this, I need your participation. So just anything. All right, so if you're here, as I've said in the past streams, I don't want to be talking to a brick wall. So if you are here, please be using the chat and let me know if you understand or don't understand. If you understand, just say yes or put a little symbol or something in the chat so that I know. Else, we'll have to end it early. All right. So I'll give you a minute to catch up, and then we'll see how many people are still here. All right, what did I say I'd do next? Files. Okay. All right, let me find an empty space and we'll do some file stuff. Still not getting lots of people, but not much interaction. All right, so from here, we're going to have a look at files. Okay, so this is kind of important. Okay, so C, we have what's known as streams. Okay, so this basically means any source of input. So that could be, for example, the keyboard that we've been doing so far, but it could also be from other locations, such as a server or other inputs, which we'll see very shortly, and also any destination for output. So we've seen things being printed to the console. It could be printed out to a printer. It could be printed out to a file. So when we've run all of our programs so far, we've had one stream in and one stream out, which was the keyboard and the screen. Now what we're going to look at is multiple streams. And the way that we view a stream on Linux or Unix is always a file. Okay, so basically a lot of this stuff will look very familiar from the very first couple of weeks, because the way we treat the input stream from the keyboard is as a file. And same with printing to the screen, it's as a file. And you can actually test that out yourself if you want. So basically, we have been using the stream known as standard in and standard out, okay, which is standard input and standard output. And we've just used their default, which is the keyboard and the screen, okay. They're ready to use, okay, and we don't have to declare them, and we don't need to open or close them, but you can open them. I wouldn't recommend closing them. Okay. Now, with that, we've had access to a bunch of stuff that we can use with them. And the most obvious set is going to be printf and scanf. Okay. We also saw some others like putCar and getCar. Okay, getting a single character or putting a single character. These ones here are printing, so they're standard out, and these ones are scanning, so these are standard in. Does that make sense so far? A very quiet chat. It's kind of worrying me, especially with how many people are here. Cool. Cheers. All right. So, sorry. So basically, where'd my pen go? We are actually, when we're printing, we're actually writing data. Okay. And when we're scanning and getting to standard in, we're actually reading data. Okay. It's not the keyboards going directly to the screen, and neither is it that we're printing directly to the screen. Okay. So now what we'll go and have a look at is introducing our own streams. Okay. So that's going to be files. Okay. Now, it's the last example for part 3 of assignment wrong for current. I highly doubt it. Let me finish this and then we can have a look. But I highly doubt it. All right. So what we're going to have a look at is we can have a look at 2 different types of files. And this is important because the way that we write data will change how we read it as well. So we can have text files and we can have binary files. Okay. And you need to consider this with your standard in as well. Okay. So for example, if I wanted to store the number 32,767 to a file, okay, there's 2 ways that I could do it. I could store in 5 bytes the character 3, the character 2, the character 7, the character 6, and the character 7. Okay. And then we'd have 5 bytes in memory. Okay. And they'd be, so for example, the 3 in memory would be 0011, 0011. Okay. And so on. But we know that this number can be stored in 16 bits. So we could actually store it in the file like this. 01111 1111 1111 1111. And that there is the value 3276. But if we try and read that as characters, it's going to be utter garbage. So generally, it's better if you want to save space to store in binary. But if you need someone to be able to read that file, storing it in binary is kind of pointless. Okay, so you need to think about this. All right, because obviously, if you were going to write an essay, you wouldn't want to write it as a binary file because no one would be able to read it if it had numbers and stuff in it. Where your text file, you'd write your numbers as text. Hopefully that made sense. So now we get to the next fun one. So what I might do is, so can you tell me what's wrong with the current? And then we'll go into files. Because where's my calculator? The last example for part 3 of assignment, the current is wrong. All right, I'm checking that now, and then we'll go back to files. So someone's just asked about the assignment, and we'll double check. Assignments, assignment 2, example 3, example 3. So got currents. The addition of those looks correct, so it's only really the example. So the current for the example says 7. It's not. Oh, last example. Well, it has to be a whole number, so that makes sense. So we got. What have we got? We've got the overall. So we got 140 divided by 336, which is, yeah, it's correct. What I got. Where's the camera? It's correct. There's no complex part, so it's just 240 divided by 336, which gives you 0.7143. Make sense? That one should be the easiest to calculate because there is no reactants in that problem whatsoever. So it is just normal division, but obviously if you do it with complex, it still should come out correct. So the last one is definitely right. And I can't see anything wrong with it. So let's continue with files unless you've got something else to add. Is files making sense so far? So, all right. So from here, what we're going to do is have a look at the next guy. So the next thing we're going to look at is file pointers. Of course, you can't escape pointers. And these are a little bit different. So we have a type, okay, and it's a special type, and basically it's file star. It's not a macro, okay, it's actually a struct, but and that's part of the standard. So this is included in standard IO, okay. And so we can create file pointers. So for example, file pointer 1, file star, file pointer 2. Okay, as simple as that. Now, these are used slightly differently than the pointers we've done so far, because we're going to be using them with our file functions. Okay, and the first one that we're going to look at is fopen. Okay, so fopen is basically opening a file. Okay, so we can't do much with a file unless we open it first. So to do that, we declare our file pointer beforehand or on the same line. So I might do it on the same line so that I can scroll down. Preferably you do this on the same line because it depends if you want to check it, if it opens or not. Actually, we're not going to bother checking at the moment, but I'll add that actually. So I'll show you 2 ways of doing this. So this isn't a very good way of doing it, and I'll explain why in a second. My stuff .txt, and then I'm going to add something else here, which is going to be an R. All right. So our fopen has 2 arguments. It has the file name and it has the mode. Okay. So the mode is important because that changes how we can use our file. So this one here, R, and it's in double quotes, not single quotes, is reading. Okay. W is writing. Okay. And the file doesn't have to exist. Okay. If I can spell. So it will create a new file. A is for appending. Okay. So that means you can take a file and start adding to the end of it, which is very handy if you want to continue working on something. And same thing, the file does not have to exist. Sorry, I forgot the not. We then have R plus, which is reading and writing. Okay, but the file needs to exist. Let me just do this, this. We have W plus, which is reading and writing. Okay. But if the file exists, it truncates it. Okay. So it basically just kind of starts at the start. Okay. And just deletes everything. So you have to be careful about that. And then A plus is reading and writing, but it depends. Okay. Makes sense so far? So we've got all of these different modes, okay, that we can use. So if this is making sense, just say yes in the chat. In the very quiet chat. All right. So from here, we can pass a string as the file name as well. Okay. So for example, you could have something like this instead. So I'll just show you this because this will help with what we're going to do next. This is stuff that we've already covered, but I'll show you anyway. This should be familiar with for you. So we could do something like this. Car. Let's say file name. Let's say 50 characters, and then a printf. Please enter name of file blah, and then scanf %s file name. It's a pointer, so we don't need the ampersand, and then we could just put that there. Now, obviously, no double quotes because we don't want the word file name. We want the variable file name. Okay, and that's how we'd get the file name from the user. Okay, now from what we did before, if we wanted to get it from the command line, all we'd write here, so no user whatsoever, but this time the command line, we'd change our main so it had argc and argv, and then all we do here is argv1 or 2 or 3. Okay, and that'll allow us to do the next lab because we're going to get stuff from the command line and open files. Now, whilst this all looks good, and I can't even remember my file name, and if you run this and there's a text file, let's say called hello.txt, it all looks like it runs. But the problem occurs when, obviously, you might try and open a file and it doesn't exist. Okay, so if I try and read a file that doesn't exist, okay, then we don't want to continue, because if it doesn't exist, I can't read something that doesn't exist. So if open, when trying to read or write plus, and there's no file, it will just return a null pointer. Okay, so in that case, we can do, well, we can do it this way instead. So we can just go if ftr3, why did I call it ftr? It should have been f pointer. If pointer 3 equals null, then you can just say something like printf file does not exist. And you could either put it in a while loop so they can enter it again, which is usually the nicer way of doing it. But if you kind of want to just close the whole program down, if they spell something incorrectly, you can do it that way as well. Don't use exit here, just return gracefully. But yeah, when you've got a choice, obviously the while loop would be the best here. But that's how you deal with a file that might not exist. Now, in terms of where the file needs to be, this is from the path of the executable. So for example, if you had a folder, you can write a path here as well. So for example, let's say you were running it from the PES folder. Then you could write something like lab 6 slash, oh, why did I put quotes again? Hello.txt. I might have the thing the wrong way around, but that's okay. All right. And yeah, I think I do. It's Unix, so it should be that way. All right, so you can put a full path in here as well. You can even put ... if you really wanted to. So you can do normal path operations. Okay. Now, when you are dealing with a file, there is something really, really important to do, and this is close. So this is to close the file. Okay. So to do that, when you're finished with the file, you just close and then put the name of the file pointer in there. Now with writing, if you forget to close it, it most likely will not save all or part of the data that you've been writing to it. Okay. So it actually writes to the file on close. Okay. So you've probably seen that already. Think about Microsoft Word. If you're writing a text file and you close it and you say, no, I don't want to save, it just leaves the file alone. Okay. Same thing here. If you forget to close and you do all this writing, it's not going to write it to the file until you close it. Okay. So you need to remember at the end of your program or wherever you've finished with the file, just to close it. Okay. Is that making sense so far? I'm just trying to remember which ones I did for Lab 8. I think I made you do fopen, beautiful. Gets, beautiful. Read, beautiful. All right. So we'll start with the easy ones and then we'll get to the harder ones. All right. So what I might do now, I'm just going to take a quick 3-minute break. If you're here, please say so in the chat. And if you're listening to this and you're a little behind, skip ahead to the live portion so that you can interact. I'll be back in a second, or 3 minutes, or whatever. I don't know. So that. All right, so if you're still here, just say hi in the chat, and then we'll continue. Cool. All right, so from here, we can continue down. What am I looking at? On files. Okay, so we've opened a file, we've closed the file, and now we want to do some stuff with the file. So the very easy functions for files are going to look extremely similar to what you've done before. So the first two is fprintf, and the second one is fscanf. Okay. So let's say I've got a file and I want to open it up for writing. So file star, I'll just call it FP for file pointer, and I will fopen my file, and let's just say it's hello.txt. Okay, and in this file, I'm going to do writing. Okay, and then I'm going to go fprintf. Okay, and let's introduce a couple of variables. Int a is 4, float b is 2.2. Okay, so I'm going to go fprintf, and the difference between fprintf and printf is one little thing. Okay, the first argument needs to be the file pointer. Okay, so we just put file pointer there. Then we just use this as we have before. So I'm going to print for the very first one. I'm just going to print hello, and then a new line. Okay, I'm then going to do fprintf again. File pointer, and I want to print my int. Okay, so I'll go %d. Okay, and I might do a new line as well, just to make it clear. And that's going to be a. And then I'll go fprintf, and I'll go file pointer, and I'll do %.2 f/n, and that'll be b. Okay, so this is looking very familiar. And then I'll do fclose because I want to close the file. And then I should be able to go into my folder, and I should see a nice file there that should, if I open it up in text editor, it should have hello, 4, and 2.2. Okay. From there, I want to read this file. So I'm going to go, I'll use the save file pointer. So I'll go file pointer becomes, now I can use this because I've closed it. It's not talking about this one anymore. fopen, hello.txt. Now, normally here, if you're going to do reading, always double check that it exists. So put your if statement there to check that it exists. But I'm going to leave that out for room. And then I'm going to go fscanf, file pointer. Actually, before that, would help if I had somewhere to store it. So I'm going to create three new variables: int x, float y, and car z 50. Okay, so the last one's a character array to store a string. I've got this text file that I've just written, and I want to read it. So I'm going to go, what am I going to go? I'm going to go fscanf. Okay, I'm going to go %s. Okay, now with this, like our text from our user, okay, we can't collect something that the user is going to say in the future. Okay, or we can't collect something that the user said in the past. We need to collect what is at the current line. Okay, so the pointer's right here, and we can read hello. Okay, so we need to read hello first. We can't read the 2.2 first. There is something called seeking, where you can skip over stuff, which you'll do in the assignment and you'll do next week. But right now, we don't care about seeking. Okay, so %s, and we'll just go z. Okay, so z, this here will hold the string HELLO and the null terminator. And then we can go fscanf. I can spell, and I might do %d and do the address of x. And now x should have a 4 in it. And then fscanf %f address of y, and now it'll have a 2.2 in it. Yes, that's my x, and that's my y, and that's my z. And then I can close that file. Now, just to show you that the streams are just like files, you can do this if you want to try it out. So you can do fprintf standard out hello world. Okay, and that'll print to the screen because your screen is just a file. Okay, and same with the keyboard, you could do standard in for fscan. Oh shit, sorry, I made a mistake. I was getting ahead of myself. We forgot to specify the file pointer. That would help. So I'll just move those across, and we'll specify the file pointer. So first argument for f things is going to be file pointer. Sorry. I've been using scanf for so many weeks that even I forgot. Okay, so the file pointer will always be first, and then what you want to scan. Same with what we did up here. Okay, and we need to close FP. Sorry if I confused you there. But basically, fprintf, fscanf, the first thing should be a file pointer. Okay, and then it's just like normal. Okay, like you've normally been doing for the previous weeks. Now, okay, so that should be a file star. Make sense? Yes, no, maybe a little bit. I think we use fgets as well in the lab. If we're up to where I'm up to, let me know. Even my silly mistakes. I might steal this line here. Yeah, I need reading. Copy that. But over here, do I need it? Ah. Yep, standard out is just a file pointer. So you can do that. Standard in is just a file pointer. So yes, they are just files. Basically, the whole of the Unix system works on files, which is really nice because everything follows the same rules. All right. So the other one that we are going to use in the lab, and you could use fscanf if you want instead, but this is just another one that we do need in the lab. So I'm going to introduce another variable. So I'm going to call it car. I'm going to call it string buffer. And I'm going to make it 5 long. So the next one is fgets. This is just get string from a file. The first argument of this is not the file pointer. It's actually a pointer to where you want to store it, and it needs to be a string. Then the maximum number of characters to read, including the null terminator. And then the last argument's our file pointer. Now, what this does is it will read up to this. If a new line occurs before that, then it will just store that. Okay. So that's another way to read a string. You could do this with an fscanf as well, specifying the number of characters in the string, which we haven't covered, but I might do a quick intro to that in the lab. All right, so this is another way to read a string, okay, with fgets. Now, all of that stuff that we've been doing so far, this is all text files, okay? When you've been entering stuff from the keyboard to the screen, you're able to read it, okay? When you go printf and you print it into the screen, it prints it as characters. And we know that because we can easily read it, okay? If it wasn't printing it as characters, if it was storing it as binary and printing it to the screen as binary, we wouldn't be able to read it, okay? So this is all text file, not binary file. Now, in this week's lab, we've got a file that's mixed. So it has a bit of text and it also has a bit of binary. Well, it has a lot of binary. And so we are going to use another 2 functions. So these 2 functions, I need some more room, heaps of room, are going to be fread and fwrite. Okay, so these are basically our binary file functions. Okay, so these allow us to do binary operations to our files. Okay, so it allows us to write binary information rather than just strings. Okay, so we can write our number not as the characters 32, we can actually store the actual value 32. Okay, so it means when you open the file, you won't be able to read it, but another program can read it. All right. So let's have a look at this. What's the best way to do this? So the examples are going to be slightly hard to explain, just because we are doing binary, but that's okay. I'll show you how it works. So basically, if we wanted to read something, okay, and we can do that by calling fread, and I'm actually going to store the result as well so you can see everything. So I'll do int a fread, and what I'm going to do before that is I'm going to basically set up a space to store my data. Now, because it's binary data and everything's stored as bytes, okay, we're going to set up a pointer to read our data. So let me show you an example. Let's say I wanted to read just 2 bytes. Okay. So let's go unsigned short a short. Okay. So I want to read and I want to store it in this short. Okay. So basically how fread works is we need to specify 2 things. Okay. So the first thing is going to be a pointer. And obviously because it's reading, we need to know where that memory is. Now, with fwrite, we also do, and we'll have a look at that in a second. From there, we need to know the element size. Okay. Now, the element, okay, is the size in bytes. Okay. So here, it's going to be 2. Or you could write this as size of brackets unsigned short. The next one is the count. So if this is an array, it can read, for example, 3 of these. Here we've only got 1 short, so it's just going to be a 1. And then the last one is just our file pointer from where we're reading it from. So these 2 can get very confusing, and you do need a bit of practice to use them. You won't have to worry about them too much for this subject, but we are going to use them next week. Okay, so you need to be aware of them. Okay, so this is the element size, and this is the number of them. Okay, so for example, if I had unsigned short array of shorts and I had 10 of them, then this would look slightly different. So I'll explain what this int b and int a are in a second. Now it's an array, so I don't need the ampersand. So array short, okay, it's size 2. I want to read 10 of them, and then my file pointer. Okay, so this basically will read 20 bytes from the file. Okay, 2 times 10. This will read 2 bytes from the file because we've got 1 short. Here we've got 10 shorts. Okay, the first one needs to be a pointer. This is an array, so it is a pointer. Now this a and b, okay, that I've got here, basically this function returns the number of things actually read. Okay, and this is handy because if it returns 0, then nothing has been read. And that could be because you've reached the end of the file or an error has occurred. Okay. So this is how we read binary files. They are a little bit complex. They're not as easy as text files. They're very hard to debug compared to text files. Text files, you can clearly see plain English and read it. Here, you need what's known as a hex editor to read the file and work out what's going on. And you need to get pretty good with understanding hexadecimal if you are trying to debug this kind of stuff. Now, I give you most of this in the lab because it's not expected that you have to be extremely competent with this, but it is very interesting how it works. F-write is very similar, okay? So F-write, you can return the value from F-write, but it's not as important as the other. F-write, now, the first one needs to be a pointer as well. Okay, so we can do A short 2 1 FP, and that's just like before. Okay, so it looks very similar to fread, except we're writing 2 bytes to this file. Okay, same with fwrite here. Now, obviously, this file pointer has to be read and write. Okay, so we've got array short 2 10 file pointer. Okay, and that's how we use binary files. Now, the other thing you can do, just wondering if yeah, I won't worry about it actually. All right, is that making sense? Tell me we started at 4. All right, so let me know if it's making sense. I did have a list of what I wanted to cover. I've probably lost it. It was over here somewhere. Cool. Oh, there it is. All right. All right. I spelled that incorrect completely. All right. More preprocessor are easy. We can knock that out in 10 minutes. This one's going to be a little bit more difficult. All right. And then we might come back to fwrite and fread, and we can have a look at it with a proper file. I might be able to set something up because it is a little bit difficult. And the Indianness, the byte order stuff will help us with that. There's a little bit of dependency going on. So, all right. I'm just going to take a 5-minute break. Sorry. I'm just a little busy at the moment. If you got any questions, chuck them in the chat. I'm going through this fairly quickly because there's not many questions. But hopefully it's making sense. It's all stuff, file stuff isn't too complex. The binary file can be a pain, but once again, it's 2 functions. It's not a huge amount of stuff. The next section that we'll cover is preprocessor, and then we'll go on to byte order. Byte order is very confusing. Cool. I'll be back in a couple of minutes. All right. So let's have a quick look at some preprocessor directives. So first one that we've seen is hash define. And that hasn't been too surprising. So for example, pi 3.14. But how this works is basically, I'm not going to go through the full thing, but just simply, when you compile your code, it goes through a preprocessor, okay, and then it compiles. Okay, so if you have the file here that has, let's say, int a becomes pi, and you have hash define pi 3.14 in it, what actually happens is it goes through the preprocessor and it changes it to 3.14. Okay, and then it goes and compiles it. Okay, so the hash defines never actually really reach the compiler. Okay, they're just a macro, and so they just replace it to make it easier for you to understand. So you can do crazy things with it as well. So you could do crazy things, but generally it's not recommended. And I wouldn't definitely not recommend doing it in this subject. So you could do, I don't know, hash define crazy printf hello. Okay, and then I could write crazy. Okay, and then all it do, it would change my file so that where it says that, it puts a printf hello. Okay, and then it goes to the compiler. Okay, but that gets really, really difficult if you use it poorly. Okay. You can also see why we don't use semicolons, because you can see in that example why we did, but you can also see why we don't use semicolons, because obviously if I wrote pi is 3.14 semicolon, and I write int a becomes pi semicolon, then this will be rewritten as int a becomes pi, not pi, oh my god, I'm not thinking tonight, 3.14 semicolon semicolon. If this was inside of some math, you would have got a error. Okay, now whilst this is all well and good, there is another preprocessor directive that is really, really important, and really, really handy, and we need it for today, or not today's, not this week, but the following week. We're going to use this preprocessor directive, and this is if-def. Okay, so if-def basically will only add the stuff to the compiler if it's defined. So let's say what's a good example? So a good example might be something like let's say we want to test our code. Okay, so let's do two examples. So here, what I'm going to do is I'm going to do two examples. So on this side, I've got hash include standard IO .h, and then I've got int main, and then I've got this variable called test. Okay, and I'm going to set test to 1. Okay, and then I'm going to go int w becomes 2 times 4 plus 8. Okay, and then I'm going to go if test equals 1, printf test sent. Now, well, we might as well write the w in there. Test w equals %d w. Okay, and so on. Okay, so basically, let's say I'm doing a whole heap of complex maths. Okay, obviously this isn't complex, but I want to keep, we can imagine. And I want to test it, but I want to be able to turn the testing on and off. Okay, so I want to make that a 0 or a 1. Now, this will work, but it is slow because I need to check this test variable every single time. And also, when I'm not using it, when test is 0 for the whole program, this still needs to be stored in memory. So a better way to do this would be to actually use a preprocessor directive. Yeah. So we're going to hash define test. And then we're going to go int main. And we're going to go int w 2 times 4 plus 8 like we did before. But this time what I'm going to do is I'm going to write, I'll do it in a different color, hash if def test printf, just the same printf as before, w equals %d w, and so on. And then I write hash endif, return 0. Okay. So this is how we're going to do our testing a little bit later on. Okay. Sorry, let's go check something. And the reason that we want to use this right-hand version is because when we're testing, okay, we don't have an if statement here. What we have is this will go through the preprocessor. And what we get leave that as well. We get that, okay? And when we're not testing, so if I decided to comment this out, then what I get after pre-processing is this. And this is all that's compiled, and this is all that the executable stores. So you can see that this is a lot more powerful than using an if statement here, because it actually rips the code out if test isn't defined. If test is not defined, so if I comment out test, it doesn't actually include any of this. Okay, so it will make your file size a lot smaller. Plus, there's no if statement. It just either does it or doesn't do it. Okay, so this is your preprocessor directive, and this will help when you're doing testing, which we will do not this week, but the week after. But you're welcome to start using this if you like. It could go. Make sense? Yes, no? If you're here, please let me know. The chat's being a little weird tonight. So I really appreciate it. All right, let me go get a number. There it is. Beautiful. Now, many weeks ago, we talked about pointers. Okay. And that was a fun little thing we did. So what do we want? We want that's 8, that's 16. Should be fine. We want 1, 8. Let me just check something before I continue. I just want to make sure that I'm in range. Resources. 6, 3, 6. Yep, that works. Question from assignment 2. Sure, what's the question from assignment 2? Shoot, come on. While you ask your question, let me draw this. All right, so I want to store the number 1822112211 in memory. Okay. Now, when we did our when we did our memory diagram in lab 5, and we had that giant diagram on the board, and I didn't write the data in binary, and there was a reason for that, and the reason is because I want to discuss it now. Okay, so this is important because there's 2 ways that a computer and files can store stuff on a computer, and it's kind of irritating, but it also is helpful. I probably shouldn't have done such a big number. Oh well, whatever. No, I needed to. I could have done a lot of zeros. All right. So first things first, what I'm going to do, so in terms of your question for assignment 2, no, you don't have to. But if you want to, you can. All right, so first thing what I'm going to do is I'm going to convert this to hexadecimal because that's going to make life easier. So 6C, 9B, 39, and D3. Now, here is 4 bytes of memory, okay? And we can see here quite clearly that we've got 4 bytes of memory. Now, there's 2 types of systems. And one is called Little Indian and one is called Big Indian, okay? So, Little Indian with an E, and one's called Big Indian. Now, remember that every byte has an address. So we can call this, let's say 0x42, 0x43, 0x44, 0x45. So that's its address, okay? So they're counting up. But when we go and store this in memory, Okay. We're going to notice that the things are slightly different. What is going on? So what we'll see with our little Indian is that it actually stores everything in reverse. Okay? In terms of the bytes. So this byte comes first, but the byte itself is not reversed. Where big Indian, okay, stores everything in the correct order. Okay. Now, we can have a look at this in binary if we wanted to. So I should have put some more room. So, oh, actually, what I should have done was, actually, we'll just do the whole thing in binary. I think that's what you wanted. Now I'm stuck. Why can't I? Oh my god, stop. All right, so this is something to be aware of. And with our file that we're going to deal with in the lab, it has a bit of both. Okay. So what we should get here is, this is going to be annoying. I might write it's D's there. All right, I'll do it forward first because that will be easier. So we've got, sorry, I should have really. So we've got C, and we've got 6. So that's our 6 out of the way. And then we've got, what have we got? We've got 9. And we've got B, is that. If I make a mistake, let me know. We've got 3, that's easy. We've got 9. We've got D, which is 1101. The F here, and we've got 3 again. Okay, so that's in the order that we'd expect it to be in. Okay, so that's 6C, 9B, 39, D3. But on a little Indian system, we have 1101, 0011, 0011, 1001, 1001, 1011, So you can see that they're flipped around in terms of the bytes, but the bits themselves are not flipped around. Okay, so this is Little Indian, Big Indian. Okay, and it's something that you need to be aware of. And this is where F read and F write can get really difficult, because you can be using a Little Indian system that's F writing as a Little Indian, but you're reading a Big Indian file. And so with that, you need to convert them around. And this is why it's difficult sometimes to share files between Windows and Unix, because of this reason. And you're trying to read a Windows file in Unix and so on, it can get difficult. All right, is there any questions? I think most people are working on their assignments, so and it's very quiet in the chat, so I think I was going to go through some stuff in more detail, but I don't think it's really worth it. What we might do is just do an intro in the lab, because, yeah. All right, well, hopefully all your assignments are good. There's very few assignment questions as well. For the last part of the assignment, do your best. Remember that the values aren't that important. They're not worth that much in the rubric. Most of the marks are your memory management. So you can still get a very high mark with the values incorrect. And you can also get a very low mark with all the values correct. Okay? The purpose is not the values of the output. The purpose is our memory management. So you need to make sure that you've got no pointers pointing at the wrong thing, that you're very safe, that you aren't accessing illegal memory, whether you know it or not. Okay? Because that's where the major marks are lost. All right? So keep that in mind when doing your assignment. The values of the output, yes, they're worth a bit, but how you're doing things is important. The other thing is that if you're adding all the currents up to find the total current, you're doing it wrong. Okay. It's a good check, but if you follow the instructions, you shouldn't have to add all the currents up. Okay. Any final questions or any questions at all? Sorry to end early, but it's very quiet. So it's very boring. I guess not. Okay, it's very strange. Thank you very much, and I'll leave it there. If I remember how to close this.